Hey, BC Calc, these are your day 99 notes. Today, we are talking about improper integrals, and we'll see what we mean by that right away today. There's no warm-up questions, kind of like what we typically have here. But part of the title here is to infinity and beyond, and the reason for that is that part of our improper integrals, we're going to now see some integrals that have a bound on one end of infinity. Maybe it's negative infinity as a lower bound or positive infinity as an upper bound. So we're going to get into that towards the second half of the lesson today. But what's the issue with this first example? So if we're integrating from 0 to 1, the function radical 1 plus x over 1 minus x dx, we are going to run into an issue because according to these bounds, we know that plugging in 1 for x here would actually make this undefined. So we do have an issue at x equals 1. So when we're looking at the function that we're integrating and we're analyzing the bounds that we're integrating over, depending on what those bounds are, we might wind up running into some issues as far as if the integral is defined and if it exists or if it doesn't exist. Because I'll tell you, in this scenario, it may turn out that the integral does converge and approach some value. And then there are other instances where it will not. Now, that term that I just used, converge, versus the opposite of that, which would be diverge, maybe that gives you a hint into what we're going to be doing to evaluate these integrals. Okay. But there are two different major types of improper integrals. So we have, first of all, type A. So type A improper integrals are the integral from a to b of f of x dx, where f of x becomes infinite between a and b, or at an endpoint a and or b. So for example, if there's an asymptote somewhere over the interval from a to b, or there's an asymptote at one of the endpoints, a and or b in this case, well, that's going to be improper. So we're going to have to somehow justify in the end whether or not the integral does exist or does not exist. And I think you'll find some very surprising results as it relates to that today. So we're going to talk in a minute, once we go through the types, how we're going to fix that. Okay. But moving on to type B. For type B, if you, like I said at the beginning, have infinity in your limits of integration, that would be an improper integral as well. So it might be that we have infinity as the upper bound, negative infinity as the lower bound, or why not just both? Okay, maybe we're integrating from negative infinity to infinity. We will do an example like that in the notes today. So I'll talk about, how am I going to do this? How are we going to set this up such that we can evaluate the integral? And then finally, C is both A and B. So nothing too crazy there, but if you have infinity as one of your bounds and you have an issue where at some point over the interval from A to B or at an endpoint, you're going to approach a vertical asymptote there and go to infinity, then we would have to do really two things to make sure that we can set ourselves up to determine if the integral approaches a certain value or if it does not. Okay, so we're going to start with type A, and then we'll build in the lesson eventually heading towards type B. All right, so if that's good for the first page here, let me slide this on down so you can see type A. Okay. So for type A, if f is defined and continuous on the interval from a to b, but not on the closed interval from a to b, then for all values of c, such that c is somewhere between a and b. Okay. So let's just read this carefully one more time. F is defined and continuous on this interval where a is not included. It's not defined there, but it is defined at b. If we define some value c that's somewhere in between a and b, then we can write the integral from c to b of f of x such that we can then define this integral from a to b. So you'll see what I mean by that in a second. I'm just trying to give you guys enough time to get this all copied down here. Okay, so the integral from c to b is going to be defined so that we can define the integral from a to b of f of x by saying that it's the limit as c approaches a for the integral from c to b of f of x dx. So the way we're going to get around these cases where there might be a discontinuity or something happening at one of the endpoints, or at an interior point, okay, we can fix that as well, is we're going to establish a limit as some value c approaches the area where there's the problem. In this case, it's a. And as c approaches a, if this limit exists, okay, so if we can actually evaluate the limit for this integral, then we would say that it converges. Okay, and here's just kind of a quick visual as far as it's an open-ended interval at A, closed at B. We're going to pick some value C such that if we take the limit as C approaches A, and that limit exists, then that would be the integral from A to B of f of x dx. And hopefully this little, even this small number line-ish type visual helps to make some sense of that statement there. Okay. And then similarly, if it's continuous over the closed interval from A to B, where A is included but B is not, now we're just going to change it such that we're going to take the limit as C approaches B. If B is where the issue is, we'll plug in C for that upper bound. And it will be pretty much the same thing. It would just be the opposite, open on this end, closed on this end. As C approaches B, if that limit exists, then we say that we are converging. If the limit does not exist, then we're going to say that we diverge. Okay, it looks like we're ready for our first example. So let's go ahead and take a look at that here. Hopefully you had not too many issues copying that down. Our first example is the integral from 0 to 1 of 1 over cube root x dx. So in looking at this example, if you're thinking about is there an issue anywhere, and the issue does occur at x equals 0. Right, plugging in 0 right now would be an issue as far as making that undefined. So if 0 is where the issue is, what we're going to do is we're going to say, let's take the limit as some value c, where c is a number between 0 and 1, as c approaches 0 for the integral from c to 1 of 1 over the cube root of x dx. And if we can evaluate that integral and this limit exists, then we're going to say that this does in fact converge, and that this integral, even though we had a slight issue, that it does approach a specific value. All right. So from there, let's just write this as limit as c goes to 0. If you want to use anti-power rule here for c to 1, x to the negative 1/3 dx. So if I add 1, that's going to be 2/3. And then bring that 3/2. When you divide out front, you can bring the 3/2 all the way in front of the limit, right? That's actually a limit property. Limit of a scalar times that quantity of x to the 2/3. You can actually bring that scalar out front if you want to kind of clean that up a little bit. You don't have to do that step, but it might be nice to do so. All right, so we're going to now write with what we have left, x to the 2/3 over the bounds from 1 to c. So it's going to be 3/2 times the limit as c goes to 0 of 1 to the 2/3, which is 1, minus c to the 2/3. And this limit does exist, doesn't it? As c goes to 0, this becomes a 0. So the limit of c goes to 0 of this is 1, and then 3/2 times 1 is in fact 3/2. So everything's nice and simple when I can plug in that value of c, get the limit to exist, and then in the end determine that, yes, we have a finite area here, which is a little bit weird, because let's think about what this is conceptually. 1 over cube root x from 0 to 1, it's going to look like something over this interval where, let's say, here's x equals 1. We're finding this area. And what we're saying is that even though this is approaching a vertical asymptote at x equals 0, that as I increase towards that vertical asymptote at infinity there, at x equals 0, the graph is approaching x equals 0 faster than the area is accumulating. So because the function is kind of winning out here, that it's getting closer to line x equals 0 faster than this area can pick up, that's why in the end we will converge to this value of 3/2. Okay. Now, that won't always be the case. It really is very dependent on what this function is on the inside. Okay, maybe the area will accumulate faster than the function goes to its asymptote. So we're going to have to see that in some future subsequent examples. Maybe this one right here. Let's take a look. So we have the integral from 0 to 1 of 1 over x dx for this next example. So clearly, again, the issue is at x equals 0. So if we establish that we're going to take the limit as c goes to 0 from c to 1 of 1 over x dx, this would very quickly turn into the limit as c approaches 0 of, well, the integral of 1 over x. We know that that's ln absolute value x. So ln absolute value of x. And then we have to plug in our bounds from 1 to c there. So it's going to be the limit as c goes to 0 of, well, ln of 1 is going to be 0. So then you're going to get minus the ln of absolute value of c. Okay. And think about what's happening here. As c goes to 0 for the graph of ln of x, as c goes to 0, we're approaching negative infinity for that graph. Or if you want to think of the negated form of that, it would approach positive infinity. Okay. So this winds up being infinite. So because of that, we're going to say, all right, well, the area under this curve doesn't really exist because the area is accumulating faster this time. The area is accumulating faster, then our function can approach the line x equals 0. So by the end of this part of the unit, we're going to start discussing, how can I look at this in advance and kind of know whether or not it converges or diverges? So I want you to start looking for some patterns of functions of this form. In fact, now that you've seen 2 examples, I think you can probably try this one from 0 to 1. So next time we're in class, we're going to go over this one, see if it converges or diverges using a very similar technique to what we've seen. Okay. So what we're going to get into in the next page is we're going to look at more type A examples, but what if the problem is not at an endpoint? So for all the examples we've done so far, the problem happens to be at like x equals 0, or for the very first one today that we didn't compute, but the problem is at x equals 1. So if the problem is at some sort of interior point of the integral from a to b, well, wherever the problem is, you're just going to break it up over to 2 parts, right? So it'd be from a to, let's say, some value m, if m is where the issue is, of f of x dx, plus from m to b. So if we separate it into those 2 integrals and then establish a limit in front of both, we will be able to, in the end, decide whether or not those limits exist and whether or not there is a finite area underneath that curve. Okay. So let's see if we can apply that to the next example. Okay. So this one is the integral from -1 to 1 of 1 over x dx. And if we're thinking about just graphically what this looks like, 1 over x from -1 to 1, we get this hyperbola here, right? And if here's -1 and here's +1, we're looking at capturing that total area right there. And we do clearly have an issue at x equals 0, but x equals 0, notice how that's an interior point of these bounds. So what we're going to wind up doing in this case is we're going to break this up and do from -1 to 0 of f of x dx. And then we'll separate and say, well, let's also integrate from 0 to 1 for f of x dx. And from there, since we have that issue at x equals 0, you would introduce some limits. We would take the limit as, let's say, c approaches 0. When I go from -1 to 0, that's approaching 0 technically from the left-hand side. So you might want to introduce a left-hand limit there of -1 to 0, 1 over x dx. And then technically this other limit is approaching 0 from the right-hand side. So c approaches 0 from the right. 0 to 1 of 1 over x dx. Okay. But I'm going to cheat a little bit here. And the reason I'm going to cheat is because this integral we just did a minute ago, didn't we? The integral of from 0 to 1 of 1 over x dx is infinite. It diverges. Okay. So since we've already proven that this diverges, it turns out that this one would diverge as well. And therefore, there is no finite area from -1 to 1 for 1 over x. And I will say, isn't it weird that the areas don't just cancel? It looks like, when you look at the picture graphically, that this is going to come out to be 0. Okay, but because we're accumulating an infinite amount of area, really on both ends here, okay, we can't decide that this is going to approach 0 then. Okay, so like infinity plus negative infinity in this case is not going to come out to be 0. It turns out that this does not have a value. This diverges. Okay, and as you can see, we're going to save this one for class right here, but I want you to start thinking about in advance, okay, similar to the last one, where is the issue going to occur? How should we break up some integrals? And then we'll kind of go from there. Okay, but we'll save that one for class. All right. Not only are we going to save that one for class, we'll save this one for class as well. Okay, so this next example right here, we'll do that tomorrow when we're together. All right, we are going to move on to type B though. Type B is what we talked about with the infinite domains. Okay, so for type B, here are the cases. Okay, so we're going to set up an integral from closed interval a to infinity or negative infinity to b, or we can actually go from negative infinity to infinity. Okay, and kind of in general here, if we have from a to infinity for some function, we're going to just take the limit as c goes to infinity this time. And if this limit exists from a to c of f of x dx, then we'll say that the overall limit does converge and that we have a finite area there. Okay. Okay, so let's take a look at an example of that. If we have the integral from 1 to infinity of 1 over x squared dx, here's what we're kind of looking at here. So from 1 to infinity, there's the quick visual there. We're going to set this up as the limit as c approaches infinity for the integral from 1 to c of 1 over x squared dx. And we know the integral of 1 over x squared, it's negative 1 over x if you use some anti-power rule there with x to the negative second. So now we get this in the next step. Limit of c goes to infinity of negative 1 over x. If I plug in the upper bound of c, the lower bound of 1, we get negative 1 over c there. And then when you subtract a negative 1, it's going to become a plus 1 there. And as c goes to infinity, this is getting closer and closer and closer to 0. So this limit does exist, doesn't it? It turns out, in fact, that the area from 1 to infinity of 1 over x squared dx is 1. And the concept here is that this graph is pinching off, if you want to think of it that way, faster than the area is accumulating. So kind of comparing it to what we just saw before when we were approaching an asymptote. You know, here we're approaching a horizontal asymptote, and this graph is kind of heading towards the horizontal faster than the area can even accumulate. So this one has a finite area of 1 square unit. Pretty wild. Okay. Let's do a little bit more practice with bounds with infinity. So if I gave you the integral from 1 to infinity of dx over x, so this is going to be the limit as c goes to infinity from 1 to c of 1 over x dx, or you can just write it as dx over x again, which is the limit as c goes to infinity of, we know this integral is ln of x again. We got ln absolute value of x. Okay, plug in those upper and lower bounds. So it's the limit as c goes to infinity of ln absolute value of c minus the natural log of 1, which is 0. And as c goes to infinity, we know that this graph, ln of c, would approach infinity as well. So this goes to infinity and therefore diverges. Okay, this limit does not converge to a specific value. Therefore, we do not have a finite area from 1 to infinity for 1 over x dx. Okay. And again, you know, think about the examples that we've done that converge versus diverge. We're going to eventually summarize this and be able to pick something that we'll know in advance whether or not it converges or diverges. Okay. Here's one where infinity is on both ends of the bounds. So from negative infinity to infinity of 1 over 1 plus x squared. So when you have infinity on both ends of the bounds, you have to kind of pick a stopping place along the way. Okay, so in order to evaluate and set up our integrals, we need one finite value that we're going to stop at, and why not pick 0? That seems like a nice value to kind of break this up over. So we're going to integrate from negative infinity to 0 of 1 over 1 plus x squared dx, and then from 0 to infinity of 1 over 1 plus x squared dx. Now, this integral should look very familiar to you, right? In fact, I'll tell you that this whole thing converges to pi, which is pretty cool. So I'm going to set up the limits for you, and then I want to see if you can kind of finish this one out. But it's going to be the limit as Well, if we have negative infinity on the lower bounds, limit as c approaches negative infinity from c to 0 of 1 over 1 plus x squared dx. Whereas over here, you would take the limit as c approaches positive infinity from 0 to c of 1 over 1 plus x squared dx. Okay, keep going with each of these. You know what the integral, or hopefully you do, of 1 over 1 plus x squared at this point, and then see if you can evaluate those limits and get pi to come out in the end. So we'll go over that and finish that up next time we're in class together. All right, we've got one more to do. Let's do this example right here, the integral from negative infinity to 0 of e to the 2x dx. All right, so in this last example for the day, we'll take the limit as c goes to negative infinity from c to 0 here of e to the 2x dx. Okay. So we're going to take the antiderivative of e to the 2x. Just remember that if you need a u substitution for 2x, go ahead and do it. I'm guessing a lot of you can visualize without doing the u substitution that this is going to become e to the 2x over 2, right? And we're going to plug in our bounds of 0 and c. So it's the limit as c approaches negative infinity of, well, for the first part, when I plug in 0, e to the 0 is 1, so it's going to be 1/2 minus. Then I'm going to plug in c, so that's going to become e to the 2c over 2. And as c approaches negative infinity, if this exponent becomes very largely negative, we can write that, of course, as 1 over e to that power, which is going to get closer and closer and closer to 0. Okay, so as c goes to negative infinity, this whole term is going to go to 0, and thus 1/2 minus 0 is going to be that this converges to 1/2. Okay, so the total accumulated area from negative infinity to 0 for this function is finite, and it happens to be 1/2. All right, we are going to say this last one for class. Okay, there is one more example at the bottom there, but we have kind of a lot to recap next time we're together. But if you have questions about any of the